Look around you. I mean, really look. Every single moving car, every glowing light bulb, literally every step you take. What invisible rules are making all of that possible? Well, welcome to this explainer. Today, we are going to demystify three of the absolute most fundamental building blocks of the physical world: work, energy, and power. Whether you're gearing up for an exam or you honestly just want to understand the hidden mechanics governing, well, everything moving around you, you're in the right place. We're not just going to memorize isolated concepts here. These are deeply interconnected pieces of a massive, fascinating puzzle that dictates how our entire universe operates. So let's jump right in.
All right, let's kick things off with a little riddle to test our gut instincts. Imagine you're standing face to face with a massive, solid brick wall. You plant your feet, press your hands against the rough brick, and you push. And I mean you push with all your might. You keep going until you're sweating, panting, totally exhausted. Here's the question. According to physics, have you actually done any work?
You might be surprised by this, but in the strict, no-nonsense world of physics, you've done absolutely zero work. None at all. Notice the contrast here. If you're pushing a shopping cart and it's actually rolling down the grocery aisle, okay, you've done work because there was actual physical displacement. The object traveled a distance. But if you push that brick wall and it doesn't even budge, no matter how completely wrecked your muscles feel, zero movement means absolutely zero work. Effort simply does not equal work. Here is our rapid-fire roadmap for today's explainer. First up, defining work in physics. Then, we'll explore energy, specifically potential and kinetic. Third, we dive into the law of conservation. Fourth, we'll introduce time into the mix by defining power. And finally, some real-world applications and a master summary. Okay, part 1. Defining work in physics. So what actually is work? We need a rock-solid definition to build everything else on top of. And the crucial point is right here. Work is said to be done when a force causes an object to move through a distance in the direction of the force. Basically, you need three distinct things to happen all at once. 1. A force has to be applied. 2. The object has to actually move. And 3. This is the kicker. That movement has to be in the exact same direction as the applied force. Think of a person carrying a heavy bag while walking forward on a perfectly flat road. Their lifting force is acting upwards to hold the bag against gravity, but their movement is forwards. Because those directions don't line up, actually absolutely zero physics work is happening there. Wild, right?
Mathematically, this is beautifully simple. Work equals force times distance, or W equals FD. Don't let the math stress you out, it's super straightforward. Force is measured in newtons, and distance is measured in meters. Multiply them together, and you get the standard unit of work, the joule. So, simply put, 1 joule is literally just 1 newton of force moving an object exactly 1 meter. And that's it. That's the baseline for everything we're about to discuss.
Moving right along to part 2, energy, potential, and kinetic.
So we know what work is, but what actually makes work possible in the first place? Think of energy like currency. It's the cash you need to hand over to get any actual work done. By definition, energy is simply the capacity or the ability to do work. Without it, nothing happens, nothing moves. And because they're so intimately linked, energy is literally just the potential to do work, it makes perfect logical sense that they share the exact same unit of measurement. Energy is also measured in joules. You spend joules of energy to do joules of work.
Now, in mechanical systems, this energy currency mostly comes in two flavors: kinetic and potential. Think about it visually. Kinetic energy is the energy of active motion. If an object is moving, like a ball rolling down a hill or a fast-flowing river, it has kinetic energy. Potential energy, on the flip side, is stored energy. It's based entirely on an object's position or height. The higher you lift a heavy object off the ground, fighting against the downward pull of gravity, the more potential energy it's storing up, just waiting to be unleashed.
Let's run some quick numbers, just to show how easy this is to calculate. Take a 4-kilogram block as an example. If it's moving along at a velocity of 6 meters per second, we can easily find its kinetic energy. We just multiply 1/2 times the mass of 4 times the velocity of 6 squared. So half of 4 is 2, multiply that by 36, and that smooth calculation yields exactly 72 joules of kinetic energy. The math just clicks.
Now contrast that with a potential energy example. Say we lift a 5-kilogram object, which, by the way, is about the weight of a standard bowling ball, up to a height of 8 meters in the air. Using the standard acceleration due to gravity, which is roughly 10 meters per second squared, we just multiply mass times gravity times height. So 5 times 10 times 8 gives us a perfectly clean 400 joules of stored potential energy. That bowling ball is hovering there, holding exactly 400 joules of capacity, just waiting to do some work the second you let it go.
Which brings us to part 3, the law of conservation. Okay, so we've seen how energy is stored and how it moves, but what happens to it after the work is actually done? Does the energy just vanish into thin air? Absolutely not. This brings us to the law of conservation of energy, which is a fundamental truth of our entire universe. Energy cannot be created, and it absolutely cannot be destroyed. It merely changes its disguise. In any isolated system, the total amount of energy remains completely, 100% constant. It just relentlessly shifts from one form into another.
Think about a massive hydroelectric power station. It is a perfect, real-world example of this exact transformation story. First, you've got millions of gallons of water held high up in a dam, just bursting with potential energy. Then, the giant gates open and the water falls, transforming that potential energy instantly into rushing kinetic energy. That water then crashes violently into these massive turbines, turning the kinetic energy into mechanical energy as the blades spin around. Finally, huge generators take that spinning mechanical energy and transform it into electrical energy, the exact same energy that's powering the lights in your living room right now. The energy was never lost, it just evolved.
All right, part 4, power, which is work over time. So far, we've talked about how much work is done and the energy you need to do it. But we're missing one critical variable that really dictates how the real world operates: time. And that's exactly where power enters the chat. Power is formally defined as the rate at which work is done or the rate at which energy is transferred. Going back to our currency metaphor, if energy is the cash you spend to get work done, power is simply a measure of how fast you're spending it. The formula for this is super logical. Power equals work divided by time. P equals W over T. Because we're taking our work and dividing joules by seconds, we end up with a brand new unit of measurement, the watt. 1 watt means you're doing exactly 1 joule of work every single second. And if you've got a machine blasting through 1,000 joules a second, well, you've got yourself a kilowatt. Time literally changes the entire dynamic. Let's lock this in with one last quick bit of math. Imagine an electric motor that successfully does 2,400 joules of work over the course of exactly 30 seconds. To find the power output, we just take the total work and divide it by the time it took. 2,400 divided by 30 equals a neat, tidy power output of exactly 80 watts. To put that into perspective, 80 watts is roughly the power you need to light up one of those standard old-school incandescent light bulbs. Finally, part 5, applications, and our summary. We've systematically built up the theory today, from forces and distances, right through to energy and time. But how do these fundamental rules govern our everyday lives? Honestly, they are happening relentlessly all around you. In transportation, the heavy engines in our cars are actively converting chemical energy from liquid fuel straight into the mechanical energy that propels you down the highway. Out on the sports field, athletes are explosively spending their stored muscular energy to generate the massive power they need to sprint. And, looking to the future, renewable technologies like solar panels are just sitting quietly on roofs, silently obeying the law of conservation by transforming incoming light energy directly into usable electrical energy. Everything we've talked about today ties together right here in this ultimate cheat sheet. If you're preparing for an exam, or even if you just love having a really solid mental model of how things work, I'd highly recommend you pause and take a screenshot of this summary infographic. It perfectly maps out how work requires force and distance, how mechanical energy physically splits into kinetic and potential, how energy continuously transforms but never, ever dies, and how power measures the overall speed of the whole shebang. It's brilliant. To leave you feeling absolutely accomplished today, let's end with a direct challenge from an official WASIC exam. Ready? Which law states that energy cannot be created nor destroyed? Is it A, Newton's first law, B, law of inertia, C, law of conservation of energy, or D, law of momentum? Well, if you've been following along with us, you know for sure that the correct answer is C. The total energy remains constant. You've just mastered the fundamental building blocks of physics. But hey, think about what that truly means for a second. That energy you used to push that stationary brick wall way back at the beginning of this explainer? It wasn't destroyed, it transformed into heat, warming the air around you, rippling out into the universe forever. If energy never truly dies, where will yours go next? Keep learning, and we'll catch you in the next explainer.